Okay, I think we should start. And let's talk a little bit about the quiz. How did you find it? Difficult? A lot of work or difficult conceptually? Both. Okay. Um, had you seen? Were you familiar with the topic? Not the second. All right. Did it remind you anything that you had seen previously? Yeah, okay. We're gonna. Yes. Yes. Okay. So you will see that most of the part of the individual that had the I remember, let me see. No, it's all mixed up a little bit in my mind. The solutions, I have put them up on the web. So if you had observed the group quiz should have given you some guidance on how to solve the individual without knowing about the field. But we are going to solve it tomorrow. And I also will look to see whether we can record those lectures. I have not asked for a recording in this other room when we do the problem solving session, but we are going to cover it there. Also, as I told you, there is going to be a makeup assignment for those of you who would like to take it. It's going to be before the midterm, so you can make up, all right, for things. But what I would like you, when we solve the problem tomorrow, you will see that sometimes you don't necessarily need to solve the whole thing to be able to get an idea about some important things, all right? So knowing you will see it tomorrow, but knowing for the first, at least, let me see, for the first question and the last question, you do not have to know the exact value of the electric field. And I wanted to see, I have to tell you, I wanted to see whether you could make some extrapolations from the rectangular to the coaxial. But we're going to solve it tomorrow. So you will see how I would solve it. And then I wanted also to see, because the expression for the electric field is in the book, and I wanted to see how many people would have read that material. But in any case, as I said, so far we are moving along. You're going to have an opportunity, for those of you who worry about the grades or the points, you're going to have an opportunity to make it up for those of you who want it. And the makeup assignments will be a take-home kind of homework, but within bounds. So right now I give you a week. For the makeup assignment, I will give you a number of hours. So, but I would like you to wait until tomorrow, and then we will discuss the solution. I knew that it was going to be a little on the heavy side, but I just wanted to see how the class will do. And we have not graded yet. So what I plan to do on Thursday is that I will collect all the points that each one of you has so far accumulated, and I will show you a distribution in the class without names, just a distribution. So you have an idea. I would like to do that. I will do it 3 times in the quarter, so you see how the class is doing. Okay. Any other suggestions about that? About the quiz specifically, at least things that I can have in mind about tomorrow? All right, yes. Okay. In fact, it happens that today for the summary, I have a problem like this. All right, so what you will see is that we'll go from the summary, from the outline to the summary. Okay, and we're going to solve this problem. But as we will solve this problem, we will also summarize what we've learned about conduction currents. Because in this particular case, the dielectric that I'm giving you also has some kind of conductivity. All right, so now we are trying, you will see, as I told you in this class, we are building our knowledge brick by brick. So we'll try now to put more than one bricks together, all right, and see how the individual things we are learning are going to come together to solve more realistic problems. So in this particular case, we have a parallel plate. Let me get my notes. Parallel plate waveguide. A parallel plate waveguide, I meant parallel plate capacitor, which is nothing else but a section. So you will see later on when we talk about propagation of waves, when you take a capacitor like this, which is a parallel plate structure, and you start exciting waves that have a frequency, instead, if the sizes of these metals are large compared to the wavelength. And do you remember what a wavelength is? Is the reverse. If you don't remember it, we're going to see it, but it's a quantity inverse to the frequency. All right, so if you have a high frequency, it's like when a wave, like a sinusoidal wave, there's a full circle, full period. That parameter is called a wavelength. And if then, for example, for 1 gigahertz, which is 10 to the 9 hertz, the wavelength is 30 centimeters. If therefore you have, for 10 gigahertz, is 3 centimeters. So if you have a capacitor which is 1 centimeter by 1 centimeter, then that becomes a very large fraction of the wavelength. And instead of working as a capacitor, it works as a transmission line. All right? So when that happens, we call that a parallel plate waveguide. However, capacitors tend to be tiny, all right, compared to the wavelengths we are using. So you never have propagation. For example, if I am at 10 gigahertz or like 5, all right, if you like, which is what we have in 5G, okay? If we ever go to 10G in your generation, you're going to have 3 centimeters. If not, you're going to have, if we are in 5, you're going to have 6 centimeters, all right? But in that case, the capacitor, it will be in millimeters or will be in microns. So it's going to be so tiny compared to the wavelength that practically is like a lumped element. Yes? Usually, most of them are sine waves. But then we use sine waves, if you remember from Fourier transforms, if you use a lot of sine waves, you can create square waves, you can create triangular waves, you can do all kinds of things. But in the kinds of communications we are using, so for our cell phones, we are using sine waves, and as a matter of fact, it's a variation of a sine wave. It's not exactly, it's a Gaussian. So it's a sine wave with an envelope. And we use lots of them, many bands, all right? And we send the information in each one of those bands, and then on the sending end, because it goes fast this way better, and then we recollect those, we collect them, and then we put them, reconstruct the message. But we use sine waves or some variations of those. Okay. Some radars will use pulses, but a pulse is a superposition of many sine waves. So in any case, the sine wave is a fundamental, all right, wave, and we can make many other ones from them. Okay, so a parallel plate capacitor. We assume that a third of it is filled with a dielectric, which also has some kind of conductance. So this dielectric that has conductance is a lossy dielectric, and I will explain to you why. But it looks like this. And this here has epsilon sub d and sigma sub d. I used it for just symmetry. We did not necessarily need that here, the subscript. This one assume is W sub d. The whole side of the whole plate is W. This is H. Here we have free space. Here we have plus Q total. That's your total charge. Of course, here is minus Q, equally distributed. So it's an ideal parallel plate capacitor, which means what? That the field at the edges here of the capacitor do not see, the fields in here think like that it is infinite large. They don't see the edges. That's what it means. Okay. Then what else do we give? So we give that W is 10 millimeters. L, which is this distance, is 10. H, which is the thickness, is 2. Epsilon sub d is 9 times epsilon sub naught. And sigma sub d equals 10 to minus 4 moles per, what did I say here, centimeter. And or you are going to see it in the book as this one, you will see it as Siemens per centimeter. I have to tell you today, because I'm using this one. I mean, that's what I got used to, that's what I've learned, and I used since then. But of course, in this book and many other newer editions, they used Siemens. And when I was looking, in fact, to make sure that I understood that 1 Siemens is this 1 mole, which is 1 over ohm, all right? So 1 of these is 1 over that, okay, which is ohm. So when I was reading, it said the description that mho is an archaic version of this. And I thought, oh my God, you know, I am like a dinosaur. So, so old stuff, you don't see it in your books, but I like it because it reminds me of this myself, which is 1 over ohm. Okay, the inverse of resistance. Okay, so now with that, let's try to see what is going to happen here. Now, this is 1. We connect that to 1.1 and this 0.2. So there is a direct connection, all right, to these points. So let's, in fact, you can keep it the way it is. But what is happening in this, as we know? Let's look at what we have already seen. In this one, there is going to be an electric field, all right, here, that goes like this. Okay? And then here I can do that to know that this is the interface. All right. What happens here? Also, there is an electric field like that. And what happens to the two electric fields at the interface? This is an interface. What happens to the two electric fields at the interface? They are equal. Why is that? Because of the boundary conditions on the air dielectric interface, all right? So number one, we have observations now. So we are observing things. E naught equals E sub D. And they are all parallel. They go like that. Okay, then let's take this part. And I will take it here separately so it's a little easier to see. So this is part of the capacitor, all right? This is 1/3 of the initial, which is W over 3, the size. This is L, and that part is filled with a dielectric. And in this part, the electric field goes like that. And this part has epsilon sub D and has sigma. Let's start with what we've learned last time. If your material has a conductivity, which is per length, is given to us, what is going to happen here? What are we going to have other than, of course, the charge that accumulates here? What is going to happen in here? We're going to have additional charges, exactly, free electrons. So this is a dielectric. Any ideal dielectric would only have the dipole moments, all right? And you remember from the dipole moments, we went to polarization. So you don't have a current flowing through it, but we have charges, all right, that are in fact aligning here and there because of polarization, which eventually they reduce the electric field. All right, so if you put a dielectric inside a capacitor, because of polarization, as we said, the electric field here will be reduced. But this one does something in addition to that. It creates a current, J. And the current is going to be, the current density is going to be sigma E, all right? And E is volts per meters. So this is volts per meters. What is this? This is 1/ohm per meter, per centimeter. Assume the unit is, let me in fact put it per meter here just to simplify, per meter. 1/ohm per meter over ohm meter. So these are the units. Therefore, what is going to be this one? Amps per square meter. See? So what kind of a density is that? A current density, but we have two. We have the surface current density and then the line current density. This is a surface current density. All right? And why is it in the surface? Because it goes like this. And then we have a whole surface that is like, this is a little square, all right? And the surface here is all of this area. And the current goes like that. So what is the total current that flows from here to here? So the total current that if I were to connect these to 2 points, and in fact point 2, point 1, and point 2, what is the total current that flows through this area, the small area, the A So this is going to be A sub D area, which is nothing else but this times that. So W sub D times L. All right? That's the area of that portion of the capacitor. So the total current that flows from 1 to 2, and why did I put 1 and 2 here? Because this point here and that point there are at the same potential. All right? So practically, this metal here connects with 1 the same way this metal here connects with 1. All right? Same potential. Okay, so how much current because of this section flows from 1 to 2? I equals A sub D J. All right? And therefore, I would be this, which is 1/3 of W times L, 10 to the second times 10 to minus 6, because we have 10 minus 3 meters, 10 minus 3 meters, 10 to minus 6. And that is WL divided by 3, because it's 1/3, all right? This here, WD, is 1/3 of W. So I is going to be this area times this. And sigma, I gave it to you 10 to minus 4. All right, and this is going to be amps per meter, amps practically, because this is going to be what? Meters squared, the way I've done it, units. This is going to be amps per meter squared. So this and this is going to give us amperes. All right? Is that clear? So that's the total current. And as you can see, it's very tiny. It's very, very small. In fact, here it's going to be 10 to minus 8 divided by 3 to minus 8 amps. A very small current. And that exactly, it's appropriate, because if that were to be a dielectric, it cannot have a lot of conduction current, because otherwise it will be a conductor. And nobody will place a conductor in a capacitor. All right? So any real dielectric, like this one, this is a real dielectric, has both epsilon and sigma. And when people do design, they have to take that into consideration. Okay, so we found now how much is the current that goes through, the tiny current that goes through. But this also has an epsilon sub D. What does that mean? That while there is a little bit of current flowing through, what else do we have? We have a polarization current. So we have polarization charges, I should say. We have a conduction current going through, and we have polarization charges. Because of the polarization charges and because of the Q plus Q and minus Q, and of course here is going to be some kind of a distribution, all right, up here. And a distribution that is not going to be the total Q we had there. It's going to be a part of the total Q. So what else does this have other than the conduction current? Yes? And E. Sorry. Whatever value we have for that. Yes. Thank you. So the value of the E, which is a constant. And I have already taken the units, all right, into consideration. So let me put that as a constant here. All right, the units, this is therefore without units. Thank you. So this is going to be the current, and it's going to be a very small current, as a matter of fact, because we have already, as I said, included a dielectric that has a very small conductivity. In parallel, therefore, with this current, and maybe I have, what else I have? I have the polarization, all right? The polarization dipoles that create this polarization in the medium and changes the capacitance. So before we go there, I would like from here to finish and say, according, if you have seen in the book, and as we calculated last time, because of this J, between the points 1 and 2, I have the equivalent, an equivalent circuit element. And what kind of element is that? A resistor. Do you remember? We said that because we have a conduction current that flows through, we have a resistor here. And we found that this resistor R was L sigma area. Okay? Where L, in fact, I would say, is H, because we've used them H, the length, there is the separation. So H divided by sigma sub D, A sub D. All right, that we so from here, you can find the resistor. And if we were to substitute there for this resistor, I would find that R would be 2 millimeters, and therefore 10 to minus 3. Sigma sub D, which is 10 to minus 4, 1 over ohm, 1 over times M meters. Area, which area we said it was 100 times 10 to minus 6, all right, divided by 3 here. So I'll put 3 here. And from here, I will have this gives here a 10 to minus 3. This with that gives 10 to minus 1, all right? This with this is part of that. This with this gives 10 to minus 5. And therefore, I have R equals 6 times divided by 10 to minus 5, all right? And that is, since this is 1 over, this is 1 over meter, and this is meter square, all right? So here it was meter square. And this was a meter here. So this with that goes, and then this with this goes, and that goes into the numerator and makes it ohms. So then we find a very large resistance. And the resistance is very large primarily for the reason I've mentioned, because the conductivity is very low. Yes?
So if I'm current flowing through the capacitor, does it mean that the capacitor will discharge with time?
No, it means something else. No, what the capacitor will do, it's better to see it when I provide the equivalent circuit. All right? So what we found so far is that, and I can erase that. Can I erase this part? Yes? Okay. Don't have too much space here to write. So between 1, therefore, and 2, number 1, this capacitor has a resistor, resistance, R. Okay, we found it. What else did we say the capacitor has? Because of epsilon, because it's a dielectric, it's going to have a capacitance. And the capacitance for this C will be epsilon sub d A divided by H, where epsilon sub d will be 9 epsilon naught. Epsilon sub d, A sub d is going to be 10 to the second times 10 minus 6, and that's in meters. And H is going to be 2 10 to minus 3 in meters. And then, so let me take care of this first. So that's going to be 10 to minus 4. And with this one, it's going to be 10 to minus 7. Okay, so this one is 9 times 8.85, which is that, 10 to minus 12, all right, divided by 2 from here, times 10 to minus 7. And that is going to give a capacitance in the medium. And as a matter of fact, I think also A sub d was, and then there is going to be a 3 here, because it was 1/3 of that, the area. A sub d was 1/3 of the whole area, so it's going to be 1/3 here. So it's going to be this. And therefore, from here, you're going to find, so most probably this is going to be 4 point something, 312. You're going to find a capacitance. And then you're going to find the value in picofarads or femtofarads, all right? Depends on how small the capacitance is. All right, so now we have two things that connect between 1 and 2. We have a resistor and we have a capacitor. And let me call this capacitor C sub d to be able to differentiate for the rest of the structure, right? So we have R and we have C sub d. That's what I found so far. Do you agree with this? Any, yes?
So if my points 1 and 2 are not connected to anything, then I will not have print.
If so, here is, if we stop it here at this point, all right, what you see, this is a shunt, as we say, this is an RC. It's a shunt combination of a capacitor with a resistor. And what that tells you is that if I go and I put a charge, like I do here, I connect this with a voltage source. And by connecting this with a voltage source, say V naught, I place a positive charge on the upper plate, a negative charge on the lower plate. So I'm charging this. And then I'm losing a little bit of power here because the current that is going to flow here turns into heat. I lose that. All right, it's a resistor. Whatever goes through a resistor, you're losing it. All right. Now, if I remove, so I wait for some time, and then what happens here, can I erase that? So what happens is that if I connect this to the capacitor, at some point, the charge on this capacitor is going to come to this Q. And then what happens if I remove the source? The charge is going to, the capacitor is going to start, because of the charge, you're going to have still a current that goes through the resistor. And this, after so much time, all of the charges are going to go through the resistor, which means that what? That you're going to lose all of your charge in the resistor, and it's going to go like this. And then the time you need is going to be 1 over RC, the time constant, which in fact it tells you that in this kind of an application, if you put a charge and you turn off your source, Eventually, your resistor, all of the charge is going to go through the resistor, and it's going to turn into heat. And then so you will discharge your capacitor, which is what is happening in all circuits, because circuits, they have a lot of elements which are resistive. So you will never have a capacitor that you're going to charge with charge, and then this is going to keep it forever. That will not happen. What you want to make sure is that this does not happen very fast. So practically, the ideal will be that this happens very slowly, and then you have enough time here to pick up your charge and utilize it later. Okay? So, about your question. But as we are here, we have found, therefore, that we have an RC here. Okay, we've done with half of it. What is going to happen to the other half? The other half has air in there, which means that it's going to have only a capacitance. Okay? And the capacitance for this one, if I call C sub naught, is going to be epsilon sub naught. Whatever this is, 2/3 of W, L, and divided by H. And so that is going to give you an C naught. And then if you plug again in picofarads, because here that is going to be 8.85 10 to minus 12. So you have times 2 divided by 3 times 10 to second times 10 to minus 3 to minus 6. And then you divide everything by 2 times 10 to minus 3. And then you're going to find that in picofarads. Not exactly like that. You're going to find it in picofarads. Okay. And then what is going to be the total circuit between 1 and 2? It's going to be this capacitance, C naught. It's going to be this one, C sub D. And it's going to be the resistor. Okay? Any questions about this? Yes.
So even like in practical applications, right, for supercapacitor, does the supercapacitor also experience this kind of circuit?
Yes. Now, what do you mean by supercapacitor?
So a capacitor that has really high capacitance.
So the reason I asked is the following. Yes, if your material in there has conductivity, it's going to experience that. A lot of times when people want to, but it's going to change the RC constant. The higher your capacitor, the longer it's going to take, all right, for the charges to diffuse. All right, it's going to happen, but it's going to take a lot longer. The other thing is, a lot of times people place, if they want to even go lower than that, then you may put your capacitor in low temperatures. Every time you put a material in low temperatures, what happens is that it neutralizes, all right? So the electrons do not become this active in the dielectric. So you get lower sigma. You get lower conductivity. And people do that too. For example, in some very powerful computers, they put them in very low temperatures to reduce the losses. But everything that you are using in real life is going to have this small r in there. Okay, let me ask you this. Since we're not going to have any questions on top hat, I'm sorry for doing that, but I cannot see. It's the reflection of the light. I cannot see the time. We're not going to have top hat questions today, but I will try to solve a few problems as we move further into to the material. But before we go and move on, I would like to then ask you the following question here. Let's assume that we have this one. Coaxial. Inner conductor, outer conductor. Okay? Let's assume that we put here a dielectric. We filled it with a dielectric that is conducting, has some kind of conductivity, that's what I mean. So we have epsilon here, we have sigma. And we connect this one okay, so we'll have positive charges here. Total, we have negative charge there. The fundamentals will be the same, all right, between, since we have the charge here and a charge there, and the field, therefore, how does the field go? It will go from, and if I do it here, like a cross-section, all right, let's assume this is a cross-section of it. All right? Then, since this is metal and this is metal, the electric field, and this is plus Q here, minus Q. Now, in this one, which is different from the parallel plate, is because the plus Q distributes throughout this surface, all right? What is gonna, and then minus Q distributes through this surface. What is the, are they charge densities on these two surfaces identical? Are they or not? No. Why? Because this surface, which is practically the outside of this conductor, is smaller than this surface, which is this bigger one. All right? And how much is this surface? If this is A, it's going to be 2 pi A, and if this is L, times L. And how much is this going to be? 2 pi B times L. All right? So the charge distributions here, distributions, and there are different. However, the total charge is the same. So the electric field here goes like that. All right? What is going to happen if that has conductivity in there, the material? I will have currents that go in the same direction. So I will have a current J here, density. And this J is going to be sigma E. The relationship is going to be the same. And this current starts here and ends there. Okay? Therefore, if I'm going to find the total current, how am I going to find it? The total current is going to be just the density times the area. And because it's all symmetric, I'm going to have the same density here. All right? That's why I multiplied with the area, just simple. So that's going to be my total current. So practically, in this problem, between this one and these two, I have a resistor again. All right? Resistor that comes from this current, the conduction current, the material. And in addition to the resistor, I will have a capacitor. All right, that is the capacitor of this structure. What will happen if in this one I take half of this and I fill this with air and I fill this half with a dielectric that is also conducting? Then I will have something similar as I did for the parallel plate capacitor. Okay? So in this particular case, if I fill only half with a dielectric, then between 1 and 2, I will have a resistor from here. I will have a capacitor from half of the structure. And then I will have the capacitor from the rest of the structure that has the air. And that's therefore what is going to be the equivalent circuit. Okay? Yes?
So they will both have the same resistance?
No, the resistance comes only from here, from half of it.
Right. So what if I have two different dielectrics?
Each one of them is going to have its own resistance, okay, if you have two different dielectrics. The other question I wanted to ask you is here. Let's try to put a dielectric, but put it in a different way. All right, so let's go back to parallel plate capacitor, and then the same thing is going to apply to this coaxial. So parallel, and what I do is now that I cover half of it with a dielectric. Okay? Half of it. Epsilon sub d sigma, epsilon naught. What is going to happen here? Ideal capacitor. The electric field still goes like this. Okay? There's no doubt to that. That's not going to change. But this one has conductivity. So what is going to happen here in parallel with the E field, we're going to have a J. And if the field in here is E sub D, and then here is E sub naught, J will be sigma E sub D. Okay? And what happens to the boundary conditions here? What are the boundary conditions between here and here? That the normal components of the electric flux density are continuous. That is not going to change. All right? This is not going to change. So what will be the equivalent? So this one is going to have a resistor and a capacitor. All right? What is this going to have? Only a capacitor. So that is going to be the equivalent circuit for this. Okay? If this is one here, one on top. And you should be able to calculate those. And how are you going to calculate those? We know how to find the electric field. All right, when you have an air dielectric interface in a parallel plate capacitor. And then after you find the electric field, you find J. And then after you find J, you find the resistance, which is going to be here. And that's from the electric field, you're going to find your capacitance. And then this one, and then your capacitance here. Any questions about this? So that's how you develop equivalent circuits. Yes?
So this equivalent circuit on the right is for that parallel plate capacitor, right?
Yes.
And the equivalent circuit on
for this. But let's assume that I take this one and I also cover it, half of it like this, here air, here dielectric. So half. So if I'm going to show it like this, half here is the dielectric, and this is the internal conductor, all right? Dielectric here. What will be the equivalent circuit for that? That one, exactly. Okay? Any questions on this? Yes? What happens here, because of the polarization current, you will have charges. All right, so because it seems like, where does it come from? From zero, all right? There is no discontinuity on the current. However, you remember what we said, that when you introduce a electric field inside a material, then usually what is going to happen is two things. From the bound electrons, which are the dipoles. The dipole moments will create, if this is positive and this is negative, they will create a negative charge here and a positive charge there. All right? And because of the electric field, all of the free electrons will move up here, and all of the positive, the free now, because the material has both, this material has both bound electrons and free electrons. So the free electrons create J, all right? They flow. The bound electrons, they just create this polarization charge and stays. However, under the effect of the electric field, all of the free electrons will go up here, will try to go up there, all of the other ones will try to go down. And these are the electrons that will create the current. It's like you have a surface charge here that has been imposed in addition to that one. Yes?
So would that cause the dielectric to accumulating negative charges on the electric side of it, and we wouldn't have that effect on it?
At some point, depending on how much sigma you have. Usually for good dielectrics, this sigma is very small. So while that is going to give you a very high resistance, all right, which you have to take into account, especially for higher frequencies, it will not necessarily change the value of this much. Now, if you go to very large sigma, that means that starts becoming more of a conductor. And then if you have a very large sigma, then it becomes a different problem, all right, that needs to be solved differently, because the conductors, since they will have so many free electrons, they will then create another charge density here, which is going to impact that field, all right? And so for a large conductor, I would solve the problem differently, and I would try, as a matter of fact, to be more careful in doing the equivalent circuit. But yes, it will change. It will change eventually the upper field, because it's going to change the charge distribution so much. Yes?
So for that one, if I put a dielectric in, it will have current flowing through it. Then if I pull it out, it will be charged, wouldn't it? Because
This one. This one, if you pull it out, is not going to be charged. Eventually, in a little bit of time, this is a little bit of charge, and in a very short period of time, it's going to disappear.
right, but if it has current, it's outflowing the charge.
What, again?
It has current flowing through the dielectric.
Yes, here, because of the electric field.
Right, so the electrons are flowing out of the dielectric.
They're not flowing out of the dielectric. They stay there. They stay on the surface. These are free, they don't go out. Where are they going to go from here? No. So they accumulate here, like with the polarization current. So you worry about the fact that there is a current J that starts there. Is that your worry? Yeah. Okay. This current is, if I had, so you say, for example, how come do I have a current here that flows at 0, that comes, and then I have a 0 current here? All right, is that your worry? Because your boundary conditions for this current here does not apply.
Yeah.
Well, this current here is very small. That's what I'm trying to tell you. This is a very small current, practically almost going to 0, which, however, it cannot be ignored from here. There is no conduction current in free space. There is no such a thing. Eventually here, when all your free electrons become trapped at this point over time, and this is a problem you have to solve in the time domain, not where the way we solve it, all right? Yeah, that's why you cannot see the real physics in the problem, because we are not in the time domain. But usually what happens is that after all of your free electrons are trapped up here, then of course over time your charge, the current is going to go to 0. You're going to have only charges up here and not flowing through the material. And if you don't have charges that are flowing in here, then practically your J is going to go to 0. But to be able to see that, as well as how the capacitor discharges, we have to go to the time domain, which we have not done here. Okay? So practically what that problem tells you is not what is going to happen in steady state, but what is happening right now when you enter the material through, and then you just look at the first picture. And the other thing is that there is a continuous supply from here, all right, of charges. So if any of these charges, for example, come and stay there, all right, then what is going to happen is going to be a flow, is going to be a transfer of free electrons from here there on this interface. And that is going to probably continue. I suggest that instead of going there on this picture, we try to probably see that later if we have time, but in the time domain, to be able to see what is happening. Yes?
So why is it again that the dielectric is a capacitor and also a resistor?
Because this dielectric, you remember we said that there are dielectrics, the ideal dielectrics, lossless as we call them, they have these dipole moments. These field of those in free without any electric field. And then when you apply an electric field, those align. Okay? That's what we said. These ones, they have these, but also they have free electrons. It's a mix of free electrons and of those bound charges. And the free electrons, if you apply an electric field like this, practically the free electrons will move the other way, the free electrons will come here. All right, and then they, this is negative charge. These ones will orient themselves like this. This is negative here, positive here. I mean, meaning somewhere there are positive charges. if it's a metal. And then you will have all of this aligning like that. But the free electrons will be here. And then there will be the holes there. Now, you can, because of these holes that are just going into the metal, or right at the interface, they will cancel some of these electrons, so the source has to send more electrons in there. I mean, that's why this, and these are because of the losses you have in the material. Again, if you forget a little bit about the losses, so these free electrons under the presence of the electric field, they will keep a current that flows like that because they are going to flow up. And then these ones do not give a current, but they give the polarization charges. So this is the physics of a dielectric that has losses. So because of the free electrons, you have J, conduction current. Because of the polarization charges, you have P. You remember, which is the polarization density. And the polarization density, we said, is just a vector, which is chi E. And then we call that the susceptibility of the material. So it changes, it changes primarily. It creates a new dielectric constant, which is epsilon naught 1 plus chi. And that's epsilon for the dielectric. So physics, in terms of physics, polarization charges practically give this epsilon. Free electrons give the sigma. Sigma creates J. Epsilon creates, it changes the electric field, and of course it changes the capacitance. All right? Yes? If the dielectric is lossy, yeah? What's that? A tunnel resistance. What do you mean by tunnel resistance? A power source, yes. In circuits, you have, let's assume this one, all right? So let's assume you have this equivalent circuit connected to a source. Is that what you're saying? Yeah. Yes, a source is normally we include internal resistance because a source is a whole circuit. And then sources, even a battery has losses in there. All right, there are free electrons in the material that flow around, and then so it has a resistor. And other more complicated sources will have many transistors and many other resistors and other things, and not necessarily resistors that you place in there yourself in the design, but because of losses in the materials. Yes? No. This one is when the material touches, like the two parallel plates, all right, the resistor is going to be, you mean parallel with the capacitance? Yes. Yes.
Can you explain the difference between how you put dielectrics in the cylinder?
In where? In the cylinder. In the cylinder, you can put the dielectrics the same way like you will place them in a parallel plate capacitor. Either you place them vertically, all right, like I did before, or you will place them horizontally.
I think these ways are the same for 3-dimensional.
This is, in this particular case, this is 3-dimensional. So in this particular case, we have half of it. In the other, this one, let me just say, so 1 is here, 2 is there, and when we did half of it like this, that is equivalent to a parallel plate capacitor doing this. When we cut half of it. Yes. Oh, I know what you're telling me. Yes, this one, in fact, if you do, it's very difficult. All right. A dielectric like this.
So that's the in series one.
Yes. So I forgot to put it here. So this one that has this, all right, has this ring in there. That's going to be in series. You need to remember that to be in series, so your dielectric should not touch both conductors. If it touches both conductors, then it's in parallel. I would like you to go home and try to do this to get a sense of how you will place materials to be able to come with similar kinds of examples, all right, or equivalent circuits. For example, you can have something like that and you can have something like this, and you may want to think yourself of what kind of a placement of material will allow you to have something like that in a capacitor. Okay? Any questions? Yes?
So if we want to calculate the total capacitance of the entire circuit, we can always, so even though there is a resistor, we can still use the old method. I mean the normal method.
So the only difference between the old method without the resistor, all right, and this one is just we have a resistor here. And to find the total capacitance here, you have to find the total input impedance to this one. So practically here, all right, that has a resistor and has a capacitor. And to find the input impedance in this one, or to find how it behaves, you have to go into the time domain, or you have to go into phasors, all right? Because the relationship between V and I across a resistor and the relationship between V and I across a capacitor are not the same, all right? Do you remember those relationships? Okay, so what is the relationship between V and I if I have this one? This is V. This is I1. This is I2. And this is I, all right, that flows, I. What is the relationship between V and I1 for the resistor? I1. What is the relationship between V and I for the capacitor? Okay, V equals what? Okay, you're going to do it like that. Okay, I equals what? I2 equals C what? Exactly, C d V dt. So you cannot solve this problem here without going to the time domain to see what happens, or going to the phasor domain, which we are going to do when we have frequencies in our sources. And then we're going to be able to find it easily. Do you remember those things? You've done them in physics, phasors, a little bit? Okay. We'll come back to this. Any other questions so we move? You want a break, like 5 minutes? Okay, let's get a break before we go. 5, I don't know what you do with 5 minutes, but.